So continuing on with the space groups, recall this slide because you're going to be quizzed on this one. Okay. So the lattices alone give extinctions or systematic absences, however you want to look at it, in the reflections in the HKLs. Okay. So P, no restrictions. C, H plus K is even for all HKL. So half of the reflections are absent, and so on. Okay.
You also can use the blackboard.
I did, yeah.
View.
Yeah, I did already. Thank you. Yeah. Okay. Adios. We just said that with number one I just said. And the screw axes are going to affect reflections in what's called a zone of just either H00 or 0K0 or 00L. Okay. All the screw axes, depending on their direction, affect that grouping of reflections. The glide planes affect like H0L, HK0, 0KL, those. So that's something you can look for. But now, only the operations which involve translation actually cause any extinctions. So mirror planes don't cause any at all because they don't involve a translation. Similarly, rotations don't cause any extinctions. So that's why, in many cases, the space groups are not uniquely determined. They're not, anyway, uniquely determined by that. If you've used XPrep, the program XPrep, it suggests a space group based on some other criteria, but the main criteria are always the extinctions. But there's a slight difference between centrosymmetric and non-centrosymmetric space groups in that if you just plot the intensity versus sine theta over lambda, generally what you see is for centrosymmetric space groups, it drops off much faster than it does for non-centrosymmetric. And so there's something called E squared minus 1, which is a criterion for that. And if you look at the output for XPrep, it explains that it expects a value of 0.9 something for centrosymmetric and a lower number for non-centrosymmetric. That's the E squared minus 1 value. Let's not go where E squared minus 1 is. It doesn't really matter. It's just that it's something that is output. You look at it and you say, okay, if there's a choice between centrosymmetric and non-centrosymmetric, here, it's kind of crazy. Do you see it? Here it is. Okay. Thank you. Yeah. So, all right. So determining the space group, like I keep saying, is so important. Let's go on. Yeah, P21 over C is uniquely determined, so that's really good for half the time. Okay, so this is another chart. This one is from a textbook, the same one, Stout and Jensen, that I really like. And you notice that it's giving the extinctions as 2n plus 1 instead of 2n. So it means that if it's odd, it's absent. In the other book, the International Tables, if it's even, it may be present, but if it's odd, it is present, absent. Oh, confusing. And this is another table from Stout and Jensen that I kind of like too because it lists all the common space groups here, triclinic, monoclinic, orthorhombic. The ones that are underlined are the ones that are uniquely determined by systematic absences. And you see how many more there are of orthorhombic than there are of monoclinic. Because monoclinic is just this small number here. It also puts them in columns according to whether they are possible for optical activity, and centrosymmetric and non-centrosymmetric. So those are kind of the three things that you worry about. We'll talk about that some more. So here's an example. The orthorhombic space group P222 and PMM2, PMMM do not have any systematic absences. There's no translation. PMM2 is considered to be the standard setting, so even though the other ones give you the same result, we don't use it. And XPrep will output the correct one. Now, a lot of times there's conditions that are listed, but they're actually subsets of the main condition. So this is just another example of that. Orthorhombic space group has the condition for all HKL, H plus K plus L is even. And that's an I centering. But all of these other things below it are just subsets of that. Okay? So you can actually just ignore them. It doesn't really mean anything. Okay, last, down at the bottom here, there's these two that, you know, if we looked at the tables, you would see that they have the same conditions. One of them is non-centrosymmetric, the other is centrosymmetric. Usually there's no problem because of just knowing that, you can distinguish between one and the other. Okay, quiz for you now. What are the possible space groups that would follow from the observation, and only this observation, that for all HKL, H plus K is even? What do you think? Let me go back to the table over here. No, not that one. This one. Under monoclinic here, you see C2, Cm, and C2 over M. Can you distinguish among them? No, you can't. So none of those is uniquely determined. They're not underlined. They will all have no conditions except for the lattice centering condition alone, which is the H plus K is even for all HKL. So those three are ambiguous, you don't know. But they are different in that C2 is chiral, Cm is non-centrosymmetric, C2 over M is centrosymmetric. Yeah. Okay. And I think I mentioned this before, but just if you do need to get the point group, all you do is remove the translational part of the symmetry operation. So you convert glide planes to mirrors, convert screw axes to rotation axes. Okay, and so the example P21 over C has a point symmetry of 2 over n. And if you recall, on the International Tables page, the first page, it also gives that. So you can double check it there if you need it. Okay, so I'm just repeating myself here to say the observed structure factor is the square root of the observed intensity, and usually just FO or sometimes FOBS for short, and then the solved structure gives you the calculated structure factor, which means you're summing over all the HKLs and all the XYZs for all the atoms. And during the refinement process, you're trying to make them agree each other the best that you can using some kind of scale factor, sometimes called K, that is a scale factor, because they're not going to be on the same scale. But you scale them so that they agree as well as possible using least squares. And then finally, what you hope for is that you get a good R value. Okay. Now, there's different definitions of R values. Like there's 4 of them right now, I would say, that are floating around. But for right now, let me just point out that you're basically, the numerator is just looking at how well they agree. And so you want that number to be small, right? And then that's divided by the sum over all the observed structure factors. So a good value is about 0.05. If it's the traditional R1, which is the one where you eliminate the weakest reflections. Okay. So usually when people say R, just R, they mean this one, R1, which is unweighted, but it is scaled. You could say I is greater than 2 sigma of I, or you could say FOBS is greater than 4 sigma FOBS, whatever you want. They're the same thing, saying the same thing. So you're just basically throwing away the weakest ones. And it gives you a better looking number than if you don't throw away the weakest ones. So everyone likes that one. I think from time to time they've tried to get rid of this, but everyone loves R1, so it's not going to go away. Okay, so absorption considerations. Some people have dual instruments. I don't know if you guys here have access to a dual instrument, do you? One that switches between copper and molybdenum radiation? No? Okay. We have two of them in our lab. It's very nice because, particularly when you consider that some people want absolute configuration and some people want to use heavy elements, other people want to use organic elements, all organic, just carbon, nitrogen, oxygen, hydrogen. The choice of radiation can make a big difference in your success in getting a very nice result. And if you have a dual instrument, you can switch back and forth in minutes, as opposed to the whole day that it used to take if you switched the whole tube out and realigned it and everything and exposed yourself to X-rays in the process. You don't have to do that anymore if you have the instrument that can switch back and forth. So if you're ever in a position to advise on the choice of a new instrument, say, we want a dual instrument. Everyone loves them. So absorption is one of the problems that you encounter. And although absorption is, again, sort of a physics problem, it's pretty easy to imagine that X-rays go into the crystal, and if the atoms have an absorption edge that is high at that point, that before the X-rays can exit, some of them are going to get sort of soaked up, and the intensity will be less when it comes out the other side. It's not in here, right? It's just right out the window. No, you can't come in. So this is an old picture. I apologize how crude it is, but you see the thick line is indicating X-rays coming in, and the thin line is X-rays coming out, so they've lost some intensity. The degree of absorption is very much a function of what we call the absorption edge, and it's stronger the more electrons you have. So heavier elements generally have greater absorption, but it's not linear with respect to the periodic table, because it really has to do with electronic structure. And so one thing we have a really nice periodic table in our lab which has absorption coefficients for all of the elements, and you can glance at it right away and see for both copper and molybdenum which would be more appropriate. And like I said, it's not always intuitive. But usually the amount of absorption is expressed as a %, either transmission or absorption. They're inversely related. In this case, the equation I'm giving you is I over I0, so it's the amount of intensity that's lost, or absorption. And the equation is e to the minus mu t. Mu is the linear absorption coefficient, which is tabulated for each atom for each wavelength. I'll give you a website where you can go to and see that. And t is the thickness, or the path length. So it depends on how the crystal is actually oriented in the beam. Most crystals are not spheres, right? So some of them are long, skinny needles, and here's your mounting pin. If you mount the crystal like this, as a needle, when the path is this length, you're going to have a lot more absorption than when it's this length. So that's a consideration. People used to grind crystals. I've tried grinding them to spherical shapes. They usually shatter and they don't survive. So I think it's better to just try and mount them vertically if you can. But anyway, so let's consider what happens then if you go to consider these values. Now, International Tables Volume C has a lot of this information, but you can also get it on the web, and these values are updated constantly by computational people. The mass absorption coefficient is something that's attributed to the element itself, but the linear absorption coefficient takes into account the weighted averages of all of the elements that are present. So this equation has mu, which is the linear absorption coefficient, times the density, times the fractional weight, and then times mu over P, which is the mass absorption coefficient, over all of the elements that are present in your compound. I'll give you an example. Okay, so this is a mineral, calcium silicate. It crystallizes in a tetragonal space group. And if you just calculate from the formula the percentage of the mass of each type, you get, I mean, just, this is the atomic weight for calcium, and the percentage comes out to, total formula weight is 116, percentage is 0.345 for calcium, 0.241 for silicon, 0.414 for oxygen. So those are those high values. Then these are the mass absorption coefficients from the table for molybdenum and for copper. And per gram. Okay. So go on to the next slide and you see the calculation for molybdenum. Oh, by the way, I did find out that we can make PowerPoints of these and pass them out to you. So, but I think taking notes is a good idea anyway. I love it when you take notes. I think things go into your brain better if you take notes, rather than you just sit there passively. I know that's true, so do that. So you can calculate mu, the linear absorption coefficient. This actually ends up in the CIF. I don't know if you've ever noticed it. You don't have to calculate it yourself because it's done by the software, but maybe not a bad idea to do it anyway. And for copper radiation, it's much more. So this is a pretty heavy substance. So you would expect that molybdenum would not absorb as much as copper. Copper does absorb, in general, more than molybdenum. Okay, so let's just calculate these percentages. And I think this is really dramatic, the percentages. So this is the crystal shape. It's tetragonal, remember, so I just assumed that two sides were equal in length, but they wouldn't necessarily have to be. And then the longer side would be the C dimension. Okay. Long direction. And in the long direction with molybdenum, you get transmittance. So invert that, you get absorbance. For copper, 0.018% transmittance. Wow. I mean, you might not even see a beam exiting that crystal if you used copper radiation. I have seen cases where I've used gold in a crystal, which absorbs a lot, and really don't see anything if the crystal's too big. So if you wonder why you aren't getting much diffraction, that might be an absorption effect. Think about that. If you're mostly using molybdenum, you're missing the advantage of having copper radiation because copper has much more flux than molybdenum. So you get a higher intensity beam with copper than you do with molybdenum. So you can use correspondingly a smaller crystal, and with all organics, you get good diffraction. All right. Okay, so in the short direction, you get also a pretty big difference between molybdenum and copper. One of the most heavily absorbing elements is bromine, strangely enough. It's more absorbing than iodine, even though iodine's higher in the periodic table. So it's sometimes useful to look those things up. Okay, so going back to space groups, I just wanted to give you one little example. So this is a crystal that I did a long time ago. It crystallizes in this orthorhombic space group, P4 bar N2. And in the asymmetric unit, this is all you see, just a few atoms. But it didn't really seem logical that this was the whole molecule. And besides, if you look at the XYZ for each atom in the structure, I mean, it's refined, it has a very good R value, and it's beautiful, but this can't be all of it. So carbon that's labeled C3 has the coordinates given there. If you stare at it for a minute, you'll see that it's x and a half plus x and a quarter. All right? So that's a little suspicious. So you might wonder, okay, well, there probably is some kind of symmetry here. And if you just say, if you're using a program like XP, you just say grow and it grows. But if you want to be sure that you know the exact symmetry operation that's causing that, look at the international tables. So here's a page of the space group. And you see all the special positions down below. So some have multiplicities of 4, some multiplicities of 2. What was it again? It was x, a half plus x, a quarter. Do you see it? I realize it's a little small. It's kind of hard to see it. But right there. Okay, so that's a special position. And how special? Okay, so instead of having 8 molecules in the unit cell, you're only going to have 4 molecules in the unit cell. That's what this multiplicity is telling you. It's got a Wyckoff letter of F, and this symmetry operation is a 2-fold rotation axis along the C direction. So when you take that into account, then you see the whole molecule, which should look like that. So you see where C3 is there? And I've just numbered it so that the ones that are generated by symmetry are primed. But yeah, so right around here it rotates. It's kind of hard to see it there, though. Anyway, there'll be lots more examples like that. Okay. Another example, effect of uncorrected absorption. So this was something that, I don't remember the atoms that were in it, but I made a picture of it without making the absorption correction. It looks pretty ugly, doesn't it? You see how the thermal ellipsoids are kind of skinny? And some are kind of really small, and some are larger. And well, with experience, I think you'd definitely agree with me. This is not looking good. Yeah. Yeah. Yes. Yeah. So you get the data, you reduce the data, then you do the absorption correction. At that point, you should know the crystal system, at least. Yeah. So then you pick the Laue group that is probably the highest symmetry Laue group for that. You do the absorption correction. Okay. Another practical question. If it's really high absorption, you don't want to just use multiscan. So you need to have a diffractometer that can give you the phase indexes for the crystal. And this is called an analytical absorption correction. And it's mathematically more complicated, but it's also embedded in the software. And if you have, say you have something that's brominated and you have lots of bromine and really high absorption, it'll really make a dramatic difference to do the phase indexing kind of absorption correction. Yeah? Mm-hmm. Yes. Mm-hmm. Yeah. If you look at, okay, practical experience here, if mu times r, and mu, you just saw the calculation of mu, and r take as like the radius of crystal, maybe just an average radius. If that's more than 0.3, you usually should consider not the multiscan, but the phase indexing correction, which is also in SADAPs. It's just another choice. In order to carry it out, though, you need to have that matrix. You need to have the data that you got from, do you have that on your diffractometer? You take a video, and then you phase index the crystal. So you need to be able to input that. It's in a P4P file, and then it'll do the phase indexing. Yeah, you'll like the result. I've seen dramatic changes. I don't actually routinely do face indexing, but sometimes I will just collect the video and keep it in case I decide later that I might need it. It's not a bad idea to do the face indexing, but I don't always do it. Yeah, yeah. So let me show you the difference, though. So this is the same crystal. I just applied the absorption correction, and on the right-hand side, you see how different it looks. We're showing the anisotropic thermal ellipsoids, so that makes it look more dramatic. But they all look more kind of in line with one another, and rounder, not so skewed. So the picture on the left is an indication sometimes of other problems, but in this case it was an absorption problem. They're not exactly in the same orientation, sorry about that, but they are the same. It's the same structure. Yeah, I mean, when I say isotropic crystal, I mean a crystal that's been ground into a sphere, but that doesn't always take care of absorption anyway, because what's inside the structure is what matters. So it isn't just the shape of the crystal, but how the atoms are arranged inside, right? So even if you do grind it into a sphere, you're not going to really eliminate all absorption effects. They're going to be there. So you'll have a higher R value and poor agreement. Okay. Oh, this is also kind of showing the direction. If your absorption is really high, the thermal parameter looks too small, sort of the opposite of what you might think. Okay. Okay, now let's make it clear that you understand the difference between absolute structure and absolute configuration. If you have a chiral space group, you can get absolute configuration. I think that's logical. But what about non-centrosymmetric space groups? They do not give you, in general, they do not give you, necessarily anyway, an absolute configuration. They give you an absolute structure. And so if you have a non-centrosymmetric space group, usually, I mean, it's going to be something where there's just a lack of inversion. And you just can refine it that way, but don't expect that you're going to get an absolute configuration of the molecule just because it's a non-centrosymmetric space group. It has to be a chiral space group. So the way it's done in practice is, in the past, everyone used the FLAC parameter, and it's still pretty good. We can do that some more next week. This is the absolute structure or the absolute configuration. Both cause a breakdown in Friedels Law. Without going into all the math, there's an imaginary part, whoops, there, which for one configuration goes positive and the other configuration goes negative. And so they're making a contribution to the structure factor that's opposite, basically. It's not as dramatic for non-centrosymmetric structures unless there's a heavy atom, usually. Heavy atoms, it can be pretty different. And this, again, especially if you're near an absorption edge. Okay, that's all stated right there. So this is, not chemistry, but it's from Thomson-Rayleigh theory, and assumes that X-rays are scattered by free electrons. So some people call these dispersion effects, and I think that's probably the common term. So it's just a breakdown in Friedels Law. As chemists, you can just think of it that way. Oh, I'm sorry, I said it wrong. F prime is the one that can be positive or negative. F double prime is positive, but you lose the central symmetry. Okay, so how do you deal with this? You could get a pretty good idea of whether you have the right-handedness or not by just solving the structure and then inverting the structure which you should be able to do pretty easily, and then refine again. And the R value will either go up or go down or stay the same. So if it goes down, then you stay with the inverted structure, and that's the correct one. Okay? And you can also calculate this FLAC parameter. I don't know why that's in there. I think I got it in the wrong place, is what happened. So the FLAC parameter, you assign an X value of, it's called a free variable, to the one hand, and a 1 minus X to the opposite hand in the calculation. And then you refine that free variable. And it should refine to 0 if the hand is correct, and it refines to 1 if it's incorrect. A modification was introduced by Simon Parsons a few years ago, and so like the ShellX software outputs both calculations. They usually agree, but the Parsons one will have a better standard uncertainty, a lower standard uncertainty. I've never seen them disagree. I think because you look at the Parsons values and they look like they have better standard uncertainty as you believe them, maybe. But they seem fine, both of them. Just two ways of doing it. I can give you references to that if you're interested. And I mentioned this before. You shouldn't actually average the Friedel opposite strain processing if you think it might be chiral, because it might not be correct. And this is one of the websites that gives the X-ray absorption edges. At least it did the last time I checked. I should double check that. I'm sorry, this format got messed up, but these are the edges going down, the K, L, M edges, and the angstroms at which the absorption edges occur are calculated based on the KeV. And so you can compare your X-ray wavelength with these wavelengths in angstroms and decide if maybe you can avoid a place where the absorption is very strong. For instance, I had fixed this once, but I guess I got the wrong slide. Molybdenum is about 0.7 angstroms. And so, if this is for gold, 0.7 works pretty well for gold. So you don't need to worry about it. The nice thing about a synchrotron, though, if you ever get a chance to use one, is that you can dial the wavelength that you want. You don't have to, you're not restricted to just molybdenum or copper. Usually you can go down to about 0.6 angstroms X-ray wavelength, and go as high as a little more than copper, maybe 1.7 angstroms, and every way in between. So it's very useful. Now, you should ask me. Oh. No, it's completely different. It's completely different. I'll give you a nutshell explanation because we're running fast here. So these were usually linear accelerators a long time ago. You know about these. Maybe you had particles going through linear accelerators. In a synchrotron, the linear accelerator has been modified so that it's now a circle. Okay, and then there's a booster that puts electrons into the ring, and the electrons are spinning around this ring. But you have to have magnets at certain points to keep the electrons in the ring. And every place there's a magnet, there's also a stream of electrons coming out linearly as a result of this curvature and the change in energy at the curve. So they put these beam lines in where people can collect that X-ray radiation. And then you have different kinds of X-rays. Some are called hard, some are called soft. All kinds of experiments are going on. It's really pretty cool. I'll show you some pictures of the synchrotron that I go to a lot, but I've been to many of them. From here, the closest might be in Japan, I'm not sure. They just put one in China, in Shanghai, China. It's brand new. Yeah. There's one in Switzerland, there's one in Australia, Canada. Yes, yeah, yeah. So they're all over. Of course, they're really expensive to run, so scientists have to be all the time justifying the fact that they're costing the government so much money. Like the ones in the US are mostly supported by the Department of Energy, of all things. And what do we have to do with energy? Well, we just call it basic science, you know, and hope that they'll support us. The majority of the beamlines are used by protein crystallographers. Usually there's only maybe one small molecule line. But anyway, I think there's only one more slide on this page, on this thing. No, two more. Okay. So pretty soon we're going to actually go through the whole shebang of doing the structure determination. I want to talk about selecting a good crystal, even though you may not be the person who finally selects the crystal, but I want to talk about that somewhat. Anyway, you can put them under the microscope probably and see if you have a good batch. So then the pattern's collected, and the software is used again to, what we say, reduce or integrate the data. And at that point, you usually have a unit cell. You can determine the unit cell crystal system based on, you know, the geometry. Then you, the output of that is HKL intensity and sigma intensity after you've done the absorption correction. So then you determine the space group, usually running a program like XPrep or similar program. Solve it, and there's such fast solution programs now, it's unbelievable. Refine, now that could take a little longer. Usually you can get a crude result fast, but to get the final refinement, including nasty solvent and things like that, may take a day or two. In the last cycles of refinement, you introduce a line that says ACTA, and that causes it to output something called a CIF file, crystallographic information file, which has this unbelievably complicated syntax, but we're stuck with it, I think, because now the archives all have used CIF now since about 1999, and it's too hard to change. And this is where your friendly crystallographer may be a big help to you, especially when you go to check the CIF. Now, checking the CIF also is disappointing in a way, because there's always complaints called alerts about things that you did. Sometimes you can explain them away. And in fact, I think maybe only 1% of the time have I written a CIF, checked it, and had the response, "Congratulations, your CIF is perfect." But I was an editor for ActaCrystal for 12 years, so I've really done a lot with CIFs, and I can help people very easily. Anyway, once you get the checking routine to say you're done, or you've satisfied it that you've thought of everything, but there's just some things that won't go away, you're sorry, but the beam stop was in the way, or something like that, you know, some excuse. Meanwhile, you're graphically enjoying the structure. I think it's an awfully important step. I should have put it in here. Before you even write the CIF, you should probably draw a picture. Make sure that you like the packing that you have, because you have the option of moving molecules by these symmetry operations, right? Like if you want to emphasize a particular hydrogen bond, you want to make sure that your hydrogen bond donor is sitting next to the hydrogen bond acceptor. It could be here, but if it's closer, then you can actually see the bond, and that's the way you want to see it, right? So that's the fun part, in a way, is making the graphics, I think. The nasty part is making the CIF, and we're stuck with it. Sorry about that, but it keeps the crystallographers employed. And lastly, I found this cartoon, and I thought it might be appropriate. Okay, so tomorrow I'll have some examples of ways to grow crystals, but if you have other ways to grow crystals, I'd like to hear them, so, you know, share your expertise with us all. I do think it's often just a matter of luck. But patience, care, all of these things are important. Don't try to grow crystals next to something that's vibrating, because you'll usually not be able to get big ones. Things like that, little tips, right? Yeah. You can't grow crystals like the organic chemists were taught to grow crystals, you know, where you just filter it and all you have is powder. It's not the same thing. It's a growth process, right? Okay, so let's end there. Go have fun, and I'll see you tomorrow. And I'll start sending out the PDFs. I won't send them all at once because the files might be big. But not the ones we haven't done, but the ones we have done.